Hello my friends and welcome to a new lecture about probability and statistics. In today's lecture, we want to study Poisson distribution in Python. The Poisson distribution is a kind of discrete probability distribution, and we employ this kind of distribution to model the number of events that occur within a fixed interval of time or space, with the condition that these events happen independently and also at a constant average rate. This kind of Poisson is widely used in many applications like telecommunication, biology, and queen theory. In this tutorial, we will cover definitions, properties, mathematical formulation, and also we will practice different examples along with Python code. So, based on the definition, Poisson distribution is considered as discrete random variable, and it is used to model the number of events occurring within fixed interval of time or space, given that these events happen independently and also at a constant average rate. This kind of distribution is particularly useful for scenarios where events happen independently and also at a constant average rate. The Poisson distribution describes the number of events like x that occurs in a fixed interval. You can say time or area or volume, etc., right? So these events happen independently and also at a constant rate that we call this one as lambda. For example, the number of phone calls arrive in an hour or the number of typos on a page. This distribution is defined by only one parameter, and this is lambda, and the lambda is simply the average rate of occurrence per interval, and this lambda is also greater than 0. So for the probability mass function, we have like random variable x, and this random variable x follows a Poisson distribution. Just we write x follows Poisson, and with the parameters of lambda. And these also get like x values, always non-negative integer. X can be from 0, 1, 2, and so on. So the probability mass function that x is equal to x is the e, where e is the base of the natural logarithm, and this e is something like approximately e is equal to 2.71828. This is the base of natural logarithm. Then we have lambda here, and lambda is the average rate of occurrence. Also, we call this lambda as the parameter of distribution. Then the sum of these probabilities should be equal to 1. So we can write sum of x from 0 to infinity. Probability of x is equal to sum of x is equal to 0 to infinity, and the same term e in power of minus lambda in power of x divided by x factorial is equal to e in power of minus lambda e in power of lambda, which is equal to 1, right? This e in power of lambda that you can see here, this normalizes the probabilities, and this lambda in power of x, this accounts for the rate of occurrence, and this x factorial adjusts for the number of ways or x event can occur. And for the CDF, probability of x is less than or equal to k, you can say x here, is the probability of I from 0 to x or k, e in power of minus lambda in power of I divided by I factorial. This is the CDF. So this CDF gives the probability that the number of events is less than or equal to k. There is an example here. Given a Poisson distribution with an average rate of lambda is equal to 2, and this is for customers arriving per hour, we want to find out the probability of exactly 0 or 1 customer arrives in a given hour. So if lambda is equal to 2, it means 2 customers arrive per hour on average. All right, so based on the equation says probability of x is equal to x is e in power of minus lambda in power of x divided by x factorial, right? Lambda is equal to 2. So in this case, we say probability of exactly 0. So probability of x is equal to 0 is equal to e in power of minus 2 in power of 0 divided by 0 factorial. So 2 in power of 0 is 1, 0 factorial is 1, so it will be e in power of 2, which is approximately equal to 1353. It means there is approximately 13.53% chance that no customers arrive in a given hour when the average rate is 2. Then for the case of probability of x is equal to 1, this time instead of 0 we will put 1, right? So e in power of minus 2, then 2 in power of 1 factorial, right? So this one will be 1, this one will be 2, it will be 2e in power of minus 2, which will be approximately 0.2707. So the mean, like expected value and also variance of a Poisson random variable are both equal to lambda. Then a standard deviation is simply root square of lambda. Since both the mean and variance are equal to lambda, the spread of distribution depends directly on the average rate. So it means the larger lambda implies more variability. The Poisson distribution is a kind of limiting case of binomial distribution. So if n goes to infinity, it means a large one, like for example, n greater than 150, and p goes for 0, like for example, p is equal to 0.01, then a binomial of n and p such that n p is equal to lambda, this remains constant, and the probability of x is equal to k is combination of n and k, probability of success in power of k, and probability of failure in power of n minus k. This one is the same as lambda in power of k in power of minus lambda divided by k factorial. This makes it useful for rare events over many trials. Suppose that the number of errors in a piece of software has a Poisson distribution with lambda is equal to 3. This parameter immediately implies that the expected number of errors is 3 and that the variance in the number of errors is also equal to 3. Here, question is, what is the probability that a piece of software has no error, right? So it means probability of x is equal to 0. So based on the equation, e in power of minus 3 in power of 0 divided by 0 factorial, which is e in power of minus 3, and it is approximately equal to 0.40498. Then what is the probability that there is 3 or more errors? So probability of x greater than or equal to 3 is 1 minus probability of x is equal to 0 minus probability of x is equal to 1 minus probability of x is equal to 2, right? Let me explain again. Our goal here is to find the probability that software has at least 3 errors, right? It says 3 or more. In Poisson distribution, the total probability of all possible outcomes like 0 error, 1 error, and 2 error sum to 1. So the probability of 3 or more error is the complement, 1 minus, complement of the probabilities of getting 0 error, 1 error, or 2 errors. So we will calculate the probability of, we have already for 0, this one, probability of 1. So probability of x is equal to 1 is e in power of minus 3 in power of 1 divided by 1 factorial, which is approximately 1494. And probability of x is equal to 2 is e in power of minus 3 in power of 2 factorial, which is approximately 0.2241. Right? Then probability of x greater than or equal to 3 is 1 minus sum of these 3, right? So you can say 0.498 plus 0.1494 plus 0.2241, and if you do the calculation you will come up approximately 0.5767. So it means there is probability of 57.67% of having 3 or more errors in this software. So let's go for Python coding. So for Python coding, we will import numpy as np. Then also we will go for Poisson in scipy.stats. So from scipy.stats import Poisson. Then also we need to go plotting. So import matplotlib.pyplot as plt. So here our lambda is equal to 3, right? So for the probabilities, p0 is equal to Poisson.pmf, and we go for 0 and L, right? We will do the same for p1. So p1 is 1 and lambda, and we do the same for 2. p2 is 2 and lambda, right? Then probability of greater than or equal to 3 is 1 minus, so we can go for CDF or some of them, right? We can go for Poisson.CDF, CDF of 2 and lambda, okay? Now we can print them. So we can like go for print f, and probability of x is equal to 0. Probability of x is equal to 0 is equal to probability of 0 and up to 4, and we will do the same for here, and here also we do 4f and this one, right? So probability of 0 is 0.04, right? 0.04, it's correct, and it is the same as our calculation. Now we want to plot the PMF. So for that one, we need to generate some x value. So we go for x, a range of 0 to 10. Then here, PMF, we will calculate for each x value. PMF is equal to Poisson dot PMF x values and lambda, then PLT dot bar plot x and PMF, and finished. This is the PMF plot for 0 to 10 of a Poisson with lambda is equal to 3. We can also plot the CDF, PLT.step plot, and in here x and comes some PMF. So in here we plotted one step for the CDF, and in here, so x is the area of possible values that we have, like 0 to 10. Then PMF, we have calculated already PMF, and this np.com sum, this compute the cumulative sum of the PMF, and this post, this is the argument specify how the steps are drawn, and this post means that the step occurs after each x value. So let's see another example here. A call center receives an average of 5 calls per hour. So in this case, lambda is equal to 5. What is the probability of receiving exactly 3 calls in an hour? And also, what is the probability of receiving at most 3 calls, right? So probability of x is equal to 3. It's equal to, based on the equation that we have, 5 in power of 3, e in power of minus 5 divided by 3 factorial. So this e in power of minus 5 is something like approximately 0.0067, and this 5 in power of 3 is 125, and 3 factorial is equal to 6. So this all together will approximately be equal to 0.1404. And probability of x less than or equal to 3, because here's the at most 3 calls. This one is, we use CDF, so it is equal to probability of I is equal to 0 to 3, 5 in power of I in power of minus 5 divided by I factorial. Every time 1 0 1 1 1 2 1 3, right? So 5 in power of 0 e in power of minus 5 0 factorial, plus 5 in power of 1 e in power of 5 1 factorial, plus 5 in power of 2 e in power of minus 5 2 factorial, plus 5 in power of 3 e in power of minus 5 3 factorial. And if you do all these calculations, then you will come up with approximately 0.2650. So for the Python coding of the same example, so in here, lambda is equal to 5, and we want to go for PMF of x is equal to 3, right? So probability of 3 is Poisson dot PMF. Then we will pass 3 and L, right? Then we can print it. So print f, probability of exactly receiving 3 calls is equal to P3 and 4f, right? It is 1404. 1404. Then probability of less than or equal to 3, we go for CDF. So we can say CDF of 3 is equal to Poisson dot CDF, and in here 3 and L, right? Then in the same way we can print it. So print f probability of at most 3 calls is equal to CDF 3 and with 3f, right, is 265. We can also go for plotting for different lambda values. So in this case, for example, we have NP a range of like 0 to 20, and we want to plot, for example, lambda is equal to 1 2 3 up to 9, right? So we will go for plt.figure, and like fig size is equal to like 12 and 6. Then we also go for different colors. So colors equal to plt.cm color map. This is color map, and this is color map style. So here this is a kind of color map. So np line space of 0, 1, and 9. Then for L and color in zip of range 1 to 10, because we have 1 to 9, 1 to 10, and colors, we will calculate the PMF. So PMF is equal to Poisson dot PMF x and L. Then we will plot PLT dot plot x and PMF. Then markers can be like O. Then line style can be like dash, and color, we will get the color map that we have already defined. Label, also we can go for f lambda is equal to L that we have defined, right? A range. Here we go. So this is for the Poisson distribution PMF for lambda from, so let's add legend as well. So plt dot legend. Okay, so this is lambda is equal to 1, 2, 3, 4, and so on up to 9. So you can see the PMF for different lambdas. Okay, thank you very much for your attention. In this lecture, we learned about Poisson distribution, definition, PMF, CDF, mean, variance, and also we tried different examples with Python coding. Please practice and feel free to ask me by leaving a comment below this video. Thank you and see you in the next lecture.